Image representation. From previous modules, we know that numbers and text can be represented in binary and that we use circuits to store them. But what about images? In order to store a picture in the computer's memory, somehow it must be stored as zeros and ones. This module will explain how images are stored. We have seen how numbers and text are stored in the computer memory in binary. In this section, we will learn how images, photographs, and graphic images can be stored in binary as well. To understand how the binary system is used to represent digital images, images stored in binary, requires some background on how computer displays operate. All computer screens, monitors, and television screens are made up of pixels, which are tiny picture dots laid out in a two-dimensional grid. One of the factors affecting the quality of digital images is its resolution. The resolution of an image is the number of pixels used to represent the image, or to think of it as another way, to store an image like a photograph digitally, the computer superimposes on the photograph a grid and only stores one color of information for each square on the grid. Obviously, a grid with a lot of little squares will give a better picture than a grid with just a few big squares. The density of the squares in the grid is the resolution. You may hear resolution talked about as dots per inch, DPI, as in 72 DPI, or as a grid size of 640 by 480 pixels. Bitmaps versus vectors. There are two main formats in which images are stored in the computer: bitmap, also known as raster, and vector. With a bitmap, information is stored about each pixel of the image. With a vector representation, all components of the image are stored using mathematical formulas. A vector-based image can easily be scaled, meaning you can make it bigger or you can make it smaller, without losing image quality, whereas a bitmap cannot. On the other hand, with image editing programs, you can edit individual pixels of a bitmap image. In this module, we will discuss only bitmap images. With a bitmap image, the image is stored in memory by recording some piece of binary data for each pixel of the image. Recall that each pixel contains one dot of color, and it only has one color. In order to store data for that pixel in memory, the information about that pixel's color must somehow be converted to a binary number. There are various ways to do this, with some methods requiring more bits than others. The number of bits you store with each pixel affects both the image quality and the amount of memory that will be needed to store the image. One way to store an image would be to color each pixel either black or white. Then each pixel could be stored using only one bit of data, either a 1 for black or a 0 for white. A good example is the letter A shown on the left. Note that the arrangement of the black and white pixels can create a bitmap representing a letter. Grayscale images. Another type of image is a grayscale image in which each pixel contains a shade of gray. This would be the representation used for black and white photographs. If the grayscale has 256 shades of gray, then for each pixel we need to store a binary number indicating one of 256 shades of gray. As always, the grayscale pixel information will be stored in memory, perhaps row by row. How will we convert the gray value, a number between 0 and 255, to binary? How many bits will it take? If you recall from a previous module, with 8 bits we can represent unsigned binary numbers between 0 and 255. Therefore, each pixel in a grayscale image can be stored using 1 byte, 8 bits of data. Of course, most images on the computer are not black and white, but are in color. How do we store data about colored images? Again, each pixel must have a single color, and we will somehow need to store that color in binary. There are various ways to do this: 16 color, 256 color, or RGB color, also known as true color. Each of the different ways requires a different number of bits and produces different image quality. We will see how these different formats work in the next few slides. Storing color images. With a 16 color image, every pixel has one of 16 colors. In graphic editing programs, you can specify which 16 colors to use, tailoring the colors to your particular image. With only 16 possibilities, each pixel stores a value from 0 to 15, which can be done with 4 bits. And you can see the image on the left is made out of only 16 colors. With a 256 color image, every pixel has one of 256 colors. 256 different values can be stored in 8 bits. The image on the left is made out of 256 colors. RGB color. The format that's used most often and has the best color quality is RGB color, which can represent 16.7 million different colors. With RGB colors, the color in each pixel is considered to be a mixture of shades of red, green, and blue. RGB, where the amount of each color is specified as a number between 0 and 255. We talk about RGB colors using 3 numbers between 0 and 255, where 0 means no color and 255 represents the highest amount of that color. For example, 255, means we have a 255 value of red, which means maximum red, a 255 value of green, maximum green, and a 0 value of blue. There's no blue. This color is yellow. Shades of purple could be a mixture of red and blue with no green. For example, 127, 93 would give a bluish purple since it has 127 red, no green, and 93 for its blue. To handle all these colors, color displays are based on the TrueColor RGB values method, which means various degrees of red, green, and blue are mixed together to produce the color for a specific pixel. A byte of information, 256 variations, is needed to track the percentage of red, another byte is needed for the green, and a third byte for the blue. This means that 3 bytes of information are needed for each display pixel. It also means that over 16.7 different million colors can be represented, which is more than the human eye can distinguish. This method for specifying color is used in web programming. To store an RGB color image, 3 bytes, 24 bits, are needed for each pixel. So these files can become large. For comparison, a 16 by 16 image, 256 pixels, would require 768 bytes of storage. 256 pixels times 3 bytes equals 768 bytes. A comparable image in 256 colors and 16 color would require 256 bytes and 128 bytes of memory, respectively. Check your understanding of the effect of color formats on memory storage requirements by answering these questions. So how many bytes of storage are required to store this 100 pixel image? Please pause the video, take a moment to examine how many bytes you think a 16 color, a 256 color, and an RGB color would require. Assuming you pause the video and you have your answers ready, let's go ahead and check them. So the 16 color image would require 50 bytes, 256 color is 100 bytes, and RGB is 300 bytes. File sizes and compression. With a requirement of 3 bytes of binary data to describe each pixel is defined by the amount of red, green, and blue components, and a high-resolution screen such as 1600 by 1200 pixels, it doesn't take long to see how much memory is needed to display a single full-screen image. A minimum of 5.8 megabytes, which is 5.76 million bytes. With those kinds of storage requirements, images could be a problem for computers. But this has been addressed through compression techniques, which are methods that reduce image memory requirements without sacrificing significant picture quality. Compression formats. 2 of the most well-known compression methods are JPEG and GIF. Photographs are better compressed using JPEG. Art with areas of similar colors are better compressed as GIFs. Graphic editing software allows images to be saved in either format. A JPEG image file will have a name ending in .jpg, and a GIF file will have a name ending in .gif. An image for the web has usually been compressed using JPEG or GIF. There are different levels of compression. More compression means a smaller file, but after some point, the picture quality is degraded.